Okay, so here's some notes on the reading. We're going to talk about basis, the basis of a set. So I just wanted to remind you that linearly dependent, there was a theorem that said a set of vectors is linearly dependent if and only if some vector in the list can be written as a linear combination of the vectors preceding it. A set of vectors forms a basis for a vector space. This is the definition we're going to be working with today. A set of vectors forms a basis if the vectors are linearly independent and they span the entire vector space. Okay, so remember that spanning the space means that linear combinations of those vectors can create any element of the space. And then also linearly independent. So a basis is basically a spanning set, a set that can build the entire space, but that's as small as possible. You take out any redundancies. The standard basis for Rn is the columns of the n by n identity matrix. And then here, the rules for determining whether something's linearly independent and spanning was pivot in every column for linear independence and pivot in every row for spanning. So basically, almost all the questions are going to come down to row reducing, looking at the pivots, and deciding if you have a basis or not. Does it have a pivot in every column? Does it have a pivot in every row? Okay, so then finding basis for null space and column space of a matrix, or the other thing you're going to be able to do. So for null space, augment with zeros, row reduce, write the general solution in parametric form, exactly what you did before. So we know that that general solution spans the null space, right? Because you build the whole, that is the whole solution. And it turns out the book proves that that also is a linearly independent set. So you don't have to do anything new to find a basis for the null space. Exactly what you did to find a spanning set for the null space finds a basis for the null space. But for the column space, I mentioned there were like extra vectors in there. Like the column space is a set of all linear combinations of the columns of the matrix. So you could just write the span and list all the columns of the matrix. But there's some redundancies because some of those columns might be linear combinations of the others. So in order to pull out the linear combination vectors or columns, you just row reduce the matrix A, figure out which are the pivot columns, and those are the columns you can take out from your spanning set. Okay, so you only want the pivot columns from the row reduced matrix. No, the pivot columns in the row reduced matrix tell you which columns from the original matrix to use. We'll do an example. Too many words there. Okay, so I've got two vectors here, v1 and v2. Does that set form a basis for R3? Okay, so that means, do those two vectors span R3, and are they linearly independent? So let's see what happens if I take a matrix that uses these as the columns, and I row reduce it. So when I row reduce this, I get 1, 0, 0, and 0, 1, 0. All right, so remember there are two criteria for forming a basis. 1 has to be linearly independent. 2 spans the whole set. Okay. Do I have linear independence? Yes, because there's a pivot in every column. I'll write it down. Pivot every column. But does it span R3? No, because I don't have a pivot in every row. Right, so there is some vector in R3 that I could augment with, and I would end up with 0 equals some number, so it would not be consistent. So this is no, because there is not a pivot in every row. So this is not a basis. Not a basis for R3. Is it a basis for R2? No. That question just doesn't make sense. Because those vectors live in R3. They can't span R2. Yeah. All right, I want to find a basis for the set of all vectors that look like something, something, 0. Set of all vectors that look like ST0. So a basis is a spanning set, any set that spans the entire space and is linearly independent. So I'm going to say H is the span of two vectors, and I'm going to have you help me figure out what those two vectors are. So remember, the span is a linear combination. So think of S and T as your weights, right? So if you want to have an S in this first spot, when I put an S weight on there, what needs to go there? 1. And I'll put zeros in the other spots. My T weight put on this one, I need a 1 in the middle entry. And now when I take a linear combination, put the weight S on one and T on the other, add them together, I get ST0. Okay, so I know that's a spanning set. Is it a basis? So there's an additional criteria to be a basis, and that those vectors need to be linearly independent. Are they? Yes, because one's not a multiple of the other. Okay, so we have a spanning set. Those vectors are linearly independent. I'm going to say they form a basis. They form a basis for H. They span H. Their span is all of H, and they're linearly independent. So it's a basis. It is the smallest possible set of vectors that can build your whole space via linear combinations. Does that make sense? Okay. So like I could add another vector in here. Like I could have written 0, 0, 0, right? And it would still be a spanning set, but I don't need 0, 0, 0 in there in order to build all the ST0 vectors. All right, so now we're coming back to null A and col A. I want to find a basis for the null of A. So this is exactly the same process you just did in the previous lesson. This is augment with zeros, row reduce, parametric vector form, because the spanning set turns out is also linearly independent using that procedure. So augment with zeros, and you row reduce, and you get 1, 0, 0, 0, 1, 0, 6, 2.5, 0, 5, 1.5, 0, 0, 0, 0. Okay, so then we translate these to equations. This says x1 plus 6x3 plus 5x4 is 0. And x2 plus 2.5x3 plus 1.5x4 is 0. It's just the two equations because my last row is all zeros. X1 and x2 are my only free variables. Sorry, my only basic variables. Everything else is free. So if I want to write this in parametric vector form, x1, x2, x3, x4 equals, so x3 and x4 are both free, so I'm going to have them as two parameters. And then I just have to figure out what goes in these two vectors. So x1 is negative 6x3 minus 5x4. And x2 is negative 2.5 x3 minus 1.5 x4. And then x3 is free, so I put a 1 in the x3 vector and a 0 in the x4 vector. x4 is free, so its vector gets a 1 and the x3 vector gets a 0. So those two vectors that I just wrote down, they are a spanning set. Their span gives me the entire null space. It will always also be linearly independent. So we write the answer over here. The basis for null A is these two vectors. So a basis is always just a list of vectors. It's a list of vectors whose span is the entire space and is linearly independent. All right, so to find a basis for col A, we look for pivot columns of the original matrix. So basis for col A is always made up of pivot columns of the original. Okay, so in the last lesson, we just listed all the columns of the matrix, but it turns out we don't need them all to span the space because some of them are linear combinations of the others. So you can pluck those right out. You don't need them. You can build them as a linear combination of the others. So which two columns, you can look at the work from part A here, which two columns are pivot columns? The first two. So I take the first two columns from the original matrix A. So my basis for col A is a set of vectors, the first two columns of the matrix A. -2, 2, -3, and 4, -6, 8. So those two vectors will create all linear combinations of the columns of A. I actually just don't need all of the columns. And they're linearly independent since they are the pivot columns. Yeah. Yeah. It's exactly what we were doing before, except now we're not saying span. Yeah. Because the definition of the word basis says they span the space. So like the span piece is in the definition. Yeah. Yeah. It says they span the space and they're linearly independent. Okay, so that is it for the demo portion here. You can start the group activities. You have a quiz on Thursday on 31324142. And so the more you get done here, the more time you'll have for the quiz.